In this Try Me video, we have 3 examples, the first 2 of which involve decomposing three-dimensional forces into their Cartesian components and adding them together to find a resultant. You should pause the video now and try this first problem yourself, and then resume play when you're ready to see one solution. The complications involved in three-dimensional problems include the variety of orientations of the Cartesian coordinate system and the variety of multiplanar descriptions of the orientation of the vectors in 3 dimensions. Let's first make a note of the x, y, and z system in this example. X and y are in somewhat different positions, and so to make it a right-handed system, z points down. For each of these forces, we'll begin by just noting whether their x, y, and z components are positive or negative, and then go about resolving them into the Cartesian components. So the other difference here is that we've been accustomed to looking at all of the vectors with their tails placed at the origin, and in this example, if we begin with p, for instance, its head is at the origin. We have to remember that the direction of the vector goes from tail to head. If we first examine p, and we think about it as a decomposition in tail to head addition, we note that it's got a positive component in z, since z is down in this right-handed system. It's got a positive component in y, and it's got a negative component in x. So before we do anything else, we can say that for p, we have a negative x, a positive y, and a positive z component. Now, what about the details? Well, first what we'll do is we'll think about the decomposition in pieces. We've got a decomposition in terms of planes parallel and perpendicular to the xy plane. So let's begin by noting that we have if we have a 50-degree angle off the negative z-axis here, the angle between p and the xy plane is this 40-degree angle. And what we're going to do is label this axis here. Let's label this axis A. We can think of the initial decomposition as a decomposition into the z and a directions. And I'm going to define the positive UA direction over on this side. So we'll say that this is positive UA here. So what I can say right away is that P is equal to 2 kilonewtons times cosine 40 degrees in the UA direction plus 2 kilonewtons sine of 40 degrees in K. Now UA lies in the XY plane, and we see that it makes a 30-degree angle with the x-axis here, so over here it's a 30-degree angle here. And we know for a unit vector defined in a plane that the components of that unit vector correspond to the cosines and sines of the angle theta that unit vector makes with one of the axes. So here we can see that it makes UA makes a 30-degree angle with the minus x-axis, and so we can say that UA is minus cosine of 30 degrees in I, and then plus sine of 30 degrees in J. And if we plug that in, then for P, we have minus 2 kilonewtons cosine 40 degrees cosine 30 degrees in I plus 2 kilonewtons cosine 40 degrees sine of 30 degrees in J, and plus 2 kilonewtons sine of 40 degrees in K. And evaluating those numbers, we end up with P is equal to minus 1.327I plus 0.766J plus 1.286K kilonewtons. Now if we return up to the figure, I'm going to delete some of the things that I've highlighted here around P so I can clean up my figure a little bit and we can focus on the other vectors. So for Q, we can see that its orientation is similar to the orientation for P. It's going to have a negative x component and positive y and z components. So let's just make a note of that. Q is the same as P in that it's going to have a minus x, a positive y, and a positive z component. And the method by which the orientation of Q is specified is a variation of our rise over run in 2 dimensions. It's just that now in 3 dimensions we've got a rise, let's say in z, over a run in x and a run in y. We can still get very useful information from this figure. We don't have to calculate angles directly if we remember the definitions of the direction cosine. So I'm going to focus on this representation here and bring this over to this side. We have a resultant that we can calculate from those 3 increments. If we have 1 unit in z and 2 in x and 2 in y, the resultant is still the square root of the sum of the squares, and that ends up being a value here of 3. Now it's a little bit difficult to see here, but remember that a direction angle was defined as the angle made by a vector and an individual axis. So for instance, for x, the positive x-axis is here, and our angle is this obtuse angle, but the cosine of that angle is the negative of the cosine of this angle, and so we have a direction cosine for theta x, which will simply be the ratio in this case of 2 to 3, but it will be a negative value. We can proceed in a similar fashion for the other direction cosines and have cosine of theta x is minus 2 over 3. Cosine theta y is plus 2 over 3. And cosine theta z is plus 1 over 3. So because we can write a vector q as a magnitude on a unit vector, and we know the components of the unit vector are the direction cosines, we can say right away that q is 4 kilonewtons on minus 2/3 I plus 2/3 j plus 1/3 k. And that gives us minus 2.667 I plus 2.667 J plus 1.333 K kilonewtons. Finally, if we come back and look at vector F, this is described in terms of the conventional direction angles. We have 3 angles. They're all defined off the positive axes. And so this one we can write down directly without too much additional explanation. We can say that F is equal to 3 kilonewtons cosine of 45 degrees in I plus cosine 60 degrees in J plus cosine 60 degrees in K. and that gives us 2.121 in I, 1.5 in J, and 1.5 in K kilonewtons. Our resultant then occurs from just adding the individual components in these different directions. In the I direction, we have minus 1.327 minus 2.667 plus 2.121. That gives us a net minus 1.873 I. And in J, we have 0.766 plus 2.667 plus 1.5, and that gives us plus 4.933 J. And in the K direction, we have plus 1.286 plus 1.333 and plus 1.5, and that gives us a net plus 4.119 K kilonewtons. Here we have a second example involving a Cartesian coordinate system with a different orientation, and again 3 force vectors whose orientations are specified in different ways. We once again want to decompose these vectors into their orthogonal Cartesian components and add them together to find a resultant. You should pause the video here and try the problem yourself, and then resume playing when you're ready to see one solution. We'll begin again with this three-dimensional problem by just noting the orientation of the x, y, and z components so that when we talk about individual force vectors, we can talk right away about whether those components are positive or negative. We'll begin with the force P, whose tail is at the origin and pointing towards A, and we can see that that's going to have a positive component in x, a negative component in y, and a negative component in z. Once again, for P, we have this orientation described as a rise over 2 runs, and so we have a rise of 3 over an x run of 2 and a y run of 6, and once again we can find the diagonal, and if we can find that magnitude, we can interpret the ratio of 2 over that length as the direction cosine in x, 6 over that length as the direction cosine in y, and 3 over that length as the direction cosine in z, and we'll have the appropriate signs from what we can see here in the figure. So it turns out that if we take the square root of the sum of the squares of 2, 3, and 6, that this length is 7, and so we can say that cosine of theta x is 2 over 7, cosine of theta y is minus 6 over 7, and cosine of theta z is minus 3 over 7. That allows us to write for P its magnitude, 2 pounds, on its unit vector, which is defined by the direction cosines. So that's 2/7 in I minus 6/7 in J minus 3/7 in K. Come back up and take a look at Q. Now, the head of Q is at the origin, and the direction of Q is from B to O. If we want a description of Q from tail to head, we're going to have a negative component in Z, and then a negative component in X, and a positive component in Y. So for Q, that was a negative component in X, and a positive component in Y, and a negative component in Z. This is again specified as a rise over 2 runs, and so we have a rise of 9 inches for a run in 2 in X and 6 in Y. Once again, we could identify a diagonal here across this prism, And if we take the square root of the sum of the squares of 2, 6, and 9, this distance is 11. And so we can say that for Q, cosine theta x is minus 2 over 11. Cosine of theta y is 6 over 11. And cosine theta z is minus 9 over 11. And that gives us an expression for Q, which is 3 pounds on the unit vector defined by those direction cosines, minus 2 over 11 in I, plus 6 over 11 in J, and minus 9 over 11 in K. Finally, if we go up and take a look at F, we can see that this is once again described in terms of planes that are parallel and perpendicular to the xy plane. So once again, we can define a unit vector along this axis in the xy plane. We can call that UA. And our first decomposition can be along UA and along K. And we can see from that what we'll have for F, 5 pounds cosine 45 degrees along UA plus 5 pounds sine 45 degrees along K. And since we can see that UA lies in the xy plane and makes this 30-degree angle with the x-axis, we can once again say that UA is cosine 30 degrees in I plus sine of 30 degrees in J. Using the fact that cosine 45 and sine 45 degrees are both 1 over root 2, that cosine 30 degrees is root 3 over 2, and that sine of 30 degrees is a half, we can write this out as 5 times 1 over root 2 times root 3 over 2 in I plus 5 1 over root 2 times a half in J and plus 5 times 1 over root 2 in K. Putting this all together, we have for our resultant 4/7 minus 6/11 plus 5 root 3 over 2 root 2 in I plus minus 12/7 plus 18/11 plus 5 over 2 root 2 in J plus minus 6/7 minus 27/11 plus 5 over root 2 in K, all in pounds. And if we evaluate those numbers, we end up with 3.088 in I plus 1.690 in J plus 0.224 K pounds. For our final example, we have a cube of material that's being examined by a scanning electron microscope. A small inclusion is found at point P, and the direction cosines have been determined from point A to P and from point B to P. On this basis, we're to determine the coordinates of point P. At this point, you'll want to pause and try this problem yourself. When you're ready, resume playing and you can see one solution to the problem. This problem is a bit more challenging than the previous two in that we're given partial information about relative position vectors. We're told something about the orientation of the relative position vector from A to P and about the orientation of the relative position vector from B to P, but we don't know the distances from A to P and from B to P. Those become unknowns in our problem statement. So how do we go about finding those? What we can say is that wherever P is, it's single valued. That is, it exists at some point. We have to arrive at the same point no matter how we get there. So for instance, one of the things we can do is to say that if we take the path from beginning at the origin and we go from O to A, and then subsequently from A to P, that has to be the same position as if we start from O to B and then go from B to P. We have to arrive at the same place no matter how we get there. Now we know the relative position vectors from O to A and from O to B. We can see those in the figure. What we don't know are these distances. We don't know this distance, which I'll call the length from A to P, and we don't know this distance, which I'll call the length from B to P. Those will be our unknowns in the problem statement. So what we'll do is we'll use the uniqueness of P's location This requires that ROP has to have one value whether we write it as ROA plus RAP or whether we write it ROB plus RBP. Either way, we have to arrive at the same location. Let's focus on the first expression. We can see from the figure that ROA is equal to 1 millimeter in I and 1 millimeter in K. So we'll just write this, since it's unit magnitude in units of millimeters, we'll just write ROA as I plus K. And we can see that ROB here is 1 millimeter along I plus 1 millimeter along J, so we'll write that as I plus J. In contrast, RAP is a distance we don't know, a magnitude we don't know, the length from A to P, on a unit vector whose components we do know, because those are just the direction cosines that are provided. So this is minus 0.485 in I plus 0.485 in J and minus 0.728 in K. Similarly, for RBP, we can write that as a distance we also don't know, the length from B to P, on a unit vector whose components we do know. Now, since the I, J, and K directions are mutually orthogonal and therefore independent of one another, we require all the terms in I on one side of the equation to equal all the terms in I on the other side, and similarly, all the terms in J on one side of the equation have to match all the terms in J on the other side, and similarly for K. So we end up with three different equations in front of each of the unit vectors I, J, and K. If we collect all of the I components, on the left-hand side we have an I from ROA, that's just 1. And then from RAP we have minus 0.485 times the length from A to P. And on the right-hand side we have a 1 from ROB, and we have a minus 0.667 length from B to P from RBP. In J, on the left-hand side, we have no contribution from ROA, but we have a 0.485 length from A to P from RAP, On the right-hand side, we have a 1 from ROB, and we have a minus 0.667 length of BP from RBP. And in K on the left-hand side, we have a 1 from ROA minus 0.728 length from A to P. And on the right-hand side, we have nothing from ROB, but we have a 0.333 length of BP from RBP. So now this problem comes down to solving these simultaneous equations. We'll call them 1, 2, and 3 respectively. And one of the things you'll notice right away is that we have 2 unknowns and 3 equations, which generally is something that doesn't have a solution. In this problem, it is the case that there's a relationship between the orientation from A to P and the orientation from B to P, otherwise they wouldn't intersect at a common point. And so if there truly is a unique position for P here, these 3 equations really won't be independent of one another. What we can do in a problem like this is pick any 2 of these equations, solve that system for the 2 unknowns, and then use the 3rd equation to verify that, in fact, the third equation is automatically satisfied. So we can choose whichever 2 equations we want to form the system. I will choose to solve the first 2 and then use the 3rd equation to verify my result. So if I'll just note here that if I take equation 1 and subtract from it equation 2, the right-hand side disappears because I've got the same right-hand side for both equations, and what I end up with is 1 minus 2 times 0.485 times the length of AP equals 0. And that gives me a value for the length of AP that's equal to 1.031 millimeters. And if I take that and put it back, let's say, into the first equation, and just notice that the first terms in those equations are both 1 minus, I require 0.485 times the length of AP to be equal to 0.667 times the length of BP. So if I go back to 1, I end up with the length of BP has to be equal to 0.485 over 0.667 times the length of AP, and that ends up giving me a value of 0.75 millimeters. And just as a check, I can go back to my 3rd equation and ask, is 1 minus 0.728 times the length of AP, is that really equal to 0.333 times the length of BP? And in fact, it turns out that both of those sides are equal to 0.25, so I have a self-consistent solution here. If I then take those results and substitute them back into one of the expressions for ROP, either one, I can put the results back into either one to just verify that I get the same results either way. But if I substitute these values for LAP and LBP back into my expression, I end up with a single value from ROP for either expression, and it's 0.5I plus 0.5J plus 0.25K millimeters.